This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Transmission line, and essentially it tells us how this transmission line, how a wave travels along this transmission line in terms of these fundamental components or characteristics of this transmission line. Likewise, we differentiated the voltage with respect to distance along the transmission line, and we worked out the current. And most importantly was that we defined the relationship of the positive going wave to the negative, to the positive going voltage wave to the positive going current wave as the characteristic impedance. And I re-emphasized for you that the ratio of the voltage, negative going voltage to the positive negative going current wave is equal to minus Z naught, right? And that's something that you have to remember, but if you go through the analysis, you can actually convince yourself that that is the case. And essentially, now what I wanted to ask, and just to make sure that you all had the appropriate understanding, is I said we're doing a steady state analysis, right? But I've got a forward and reverse travelling wave. What does that mean? How can I have a steady state analysis and also have forward and reverse travelling waves? What does it all mean? What am I doing? Does anyone have any ideas? Because what we said is, hey, we're doing steady state analysis, so that means this is what's happening on this transmission line at after an infinite long time, right? And essentially, we said that there's a positive going wave and a negative going wave. You know, usually when I think of waves, when I'm looking at the beach or something, you see something moving forwards and then moving backwards, but there's a temporal component, there's a time component. Whereas here, we're saying there's no time component, but there's still these forward and reverse travelling waves. What does that mean? Yes?
Like lifetime equilibrium, where we see some kind of standing wave.
Right, exactly. So we're seeing the standing waves on that actual transmission line. And that's what's important here, that here we're doing steady state analysis and we're looking at the standing wave patterns on this transmission line. And that is distinct from what we're going to do in 2 lectures' time when we're going to be looking at specifically transient analysis. Okay. Then what we moved on to was we worked out, you know, we've been talking about, you know, Maxwell's equations, and we've been talking about magnetic fields and electric fields, but all of a sudden I started to talk about transmission lines, and then all of a sudden I started to, you know, by a bit of hand waving, go from magnetic fields to all of a sudden inductance, right? So therefore the question always is, well, what's the relationship between this inductance, which is a lumped circuit component, to a concept of magnetic field, right? So what we did here was we went through the process of actually working out the relationship between magnetic field and actual inductance, right? And we worked out a relationship which shows that the inductance is related to the magnetic field on that waveguide. Now, importantly, so if I'm asking you about inductance, what is inductance then? You know it's J omega L, right? Everyone's going to say, hey, it's J omega L, J omega L. But what does that L mean? And what does it mean in terms of setting up fields and, you know, stopping the flow of current and all those important conceptual things where you look at an inductor, but it's, what's an inductor actually doing? Yes?
It is energy.
What kind of energy? It's storing energy, absolutely. A capacitor stores energy also, right? And we're going to talk, so the question is, how is a capacitor distinct to an inductor? What kind of energy is it storing? Yeah, right, sure, exactly right. It's storing magnetic energy, right? So essentially what you're doing with an inductor is you're storing magnetic energy, and what you find is the LDI/dt is actually, once you set up the field, it's actually telling you how much voltage or what you need to do in order to be able to change the flow of that current. Or if you change the flow of that current, what's the corresponding change in the voltage, right? So all we've done so far is worked out a relationship between that there's this thing called inductance, and really what the inductance is doing is it's actually giving us a quantification of the energy stored in these magnetic fields. It's related to magnetic fields. And essentially what that allows you to do also is when you're designing an inductor, you can actually start thinking of things that you can actually do in order to increase inductance. Right, so for example, some of you that are designing chips or PCB boards, rather than necessarily going out and buying an inductor, you can actually start thinking of ways which you can actually create an inductor on your PCB board, which is actually try to create, if you look at that relationship, if you want to increase the inductance, you would try to maximize the magnetic field that particular component is actually creating. We went through and we talked about, likewise, instead of talking about a conductor, we also talked about a capacitor, and we went through and worked out the relationship for a capacitor and showed that there is a relationship between capacitance and the energy stored in an electric field. And likewise, we went through the relationship in working out the resistance, which was essentially the loss on a particular waveguide, in this particular case a coaxial cable, and work out the relationship there. And specifically what's important is, unlike the other like inductance and capacitance, what's important here is the way in which you do the integral. And it's essentially the two contours which correspond to the contour of the, in this particular case, the inner surface of the core, and also the contour along the ground sheath of this particular metallic conductor. And likewise, we went through and worked out the conductance or the loss in that particular material. And we went through and we talked about, briefly reiterated all the work that we had done in the past about loss tangents. Because there I've got the E double dash written up there, which is the complex component of the permittivity constant. And essentially what I'm showing you here is in the data sheet, usually what happens is when you look at various materials or the like, usually what people indicate is the relative permittivity and the loss tangent. Here I'm showing to you how you can rewrite the complex permittivity as a function of relative permittivity and the loss tangent in order to determine the complex component, which is essentially just epsilon dash tan delta. And then from that you can actually work out the relative conductance. Now, we went through very briefly on why we wanted to do all this stuff, and I'll leave that for you in the notes. Again, we don't want to rehash the lecture and do the lecture again. This is just a very quick overview. And then what we did was we used a particular example to illustrate everything that we know about transmission lines. And essentially what I said was, suppose you had a wave that was travelling on this particular waveguide, in this particular case a coaxial cable. I said that the wave that is travelling on this coaxial cable is a transverse electromagnetic wave. Who can tell me what a transverse electromagnetic wave is? Yep.
It's a wave, and it's the opposite from transversal electric waves, and it essentially means that it only has electric field components on one direction at the moment.
So the electric and magnetic field are perpendicular to each other, and it's travelling to a direction that's perpendicular to both the electric and the magnetic field. Right? So therefore, what it's saying is for this particular coaxial cable, the energy is travelling through the slice that I've actually drawn on the screen there. And what we did was used all these formulae that we had derived and worked out the inductance, capacitance, resistance, and conductance of a coaxial cable. And then what I did was indicated to you that, hey, what you're able to do is a lot of these properties where you're determining the resistance, capacitance, inductance, and resistance, conductance, inductance, and capacitance of these particular waveguides. What we can do is actually work them out for example, a coax, a two set of wires, and parallel plates. And what I wanted to emphasize to you all was essentially, if you see a couple of parallel plates, all of you know how to calculate the capacitance. That's usually one of the very first problems that you learn in electromagnetism, and probably the very first thing that they teach you when you're doing your first year physics course. But what they don't go through is potentially that those two parallel plates also have an inductance. We did that briefly in the first lecture where we had a cavity, and I showed to you that if you produce a cavity, that because of the Maxwell-Ampere relationship, essentially, and the displacement currents, essentially what you have is every set of parallel plates not only has a capacitance, it also has an inductance. It's something that's fundamental to whenever you set up such a system and you excite it. And essentially what it does is also sets up a self-resonant frequency for that particular structure, which essentially tells you that there is a maximum frequency at which you can operate that structure. Right? Because if you think about it, at the self-resonant frequency, the impedance goes to infinity, but also it means that you now start having a significant portion of inductance relative to your capacitance. Right? So essentially what I'm trying to say here is there are these fundamental relationships, and it's important for you to be familiar with them. Now, we started off, but we didn't go into all the details about, as engineers, usually everything's 50 ohm, right? You go buy a piece of equipment and you look at the input port, it says 50 ohm. Somebody's designing a chip, and you're having a discussion and everyone goes 50 ohm, and you're like, well, why 50 ohms? Why 50 ohms? Where does that come from? And is it relevant to what I'm trying to do? Right? And that's something that's absolutely important. All right, we'll go into greater details about impedance matching, but there's nothing particularly important about 50 ohms. And what we'll do is we'll derive, the history of where this 50 ohms came from or comes from. And essentially, what we've got is a coaxial cable, right? And so essentially, this is where it all comes from. So just for everyone's little bit of history, has anyone seen one of those old TVs that you plug a coax in the back of it in order to connect to the antenna? Yes? Anyone else? Yes? Yes? Okay, so there's a few of you that have seen one of those old TVs, because most of these, a lot of students these days say, well, I only watch on my computer, so I don't really know I don't usually have a TV, or if I have a TV, I plug Foxtel or whatever into it, and I don't particularly. But essentially, what happened is you would have a port in the back, and you would have a piece of coax that you would plug into it that would connect your antenna. Now, if we go through the analysis, and we'd gone through and talked specifically about this coaxial cable, and if you remember very briefly, I had derived for you the electric and magnetic fields, right? And if you've got if we look at the maximum magnetic electric field for this particular coax, what we're able to do is go through the process, and we can work out, the impedance, right? So if you neglect a few things and the like, you can actually quite quickly show that the impedance, or the characteristic impedance of this coaxial cable, goes approximately as 60 on the square root of the relative permittivity of the dielectric in the core of that particular coaxial cable. And of course, the other thing that you know is that power is V squared on R, right? And in this particular case, it's V squared on the characteristic impedance. And we know that V is related to the maximum electric field, and that's why I'd written that up on the board, or on the slides, I should say. So what we can actually do is we can say that the power is proportional to V squared and Z naught, and given the relationships that we got for E max and also for the characteristic impedance, we can rewrite that in terms of the relative permittivity, the maximum electric field, the inner core radius, the log of the outer core radius to the inner core radius on 60. All I've done is I've just put all that information into one equation. And then what we say is, well, suppose I want to work out the radius of the core conductor, which allows me to carry the maximum power, right? So what would I do there? In order to work out the minimum and maximum of some equation, what do I need to do with respect to some quantity? Right, I've got to take a derivative. Who doesn't know that? Everyone knows that? You have to, yeah, okay, so you take the derivative, and after a little bit of mathematics, what you can actually show is that that derivative has a maximum, or has a stationary point, which corresponds to a maximum, when the ratio of the outer core diameter to the inner core diameter equals to the square root of E, like where E is 2.713, right? So if we resubstitute B on A to being equal to E to the half, what we can do is find the equation for the impedance, which gives us a maximum power, and it's just 30 on the square root of the R. And in particular case, if it's an air field dielectric, what's the relative permittivity of air? 1, right? So therefore, what it says to you is, in order, if you had an air core coaxial cable and you wanted to get the maximum power, what you need is for that to have a characteristic impedance of 30 ohms. Okay. Okay, so it's 30, not 50. What's going on here? Maybe it's not to do with maximum power. Maybe it's got to do with minimum attenuation. So let's look at what happens at minimum attenuation. Okay, so what I'll do there is essentially, for this same piece of coaxial cable, I'll work out the propagation constant, and in order to simplify the mathematics a little bit, I'll make that term G, which is the shunt conductance, to equal to 0. After I do a little bit of analysis and rewrite it, I can write the propagation constant, which is the real part plus J beta, as follows, and therefore that gives me the real part as R on Z naught. Now, I'm going to assume, because it's air field, that most or all the loss is due to skin effect, right? I mean, if we had a different dielectric material, what would be the total loss? It would be the loss due to skin effect and the loss due to dielectric loss, right? So you've got a dielectric in there, right? In this particular case, it's air, so you don't have a dielectric loss. You know, I mean, technically I'm assuming it's vacuum, but you know, for air and vacuum, the relative permittivity and the relatively loss are almost exactly the same. So first order approximation, excellent approximation. So I can actually use my formulae for the resistive loss, and it's just 1 on 2 pi delta sigma, where delta is the skin depth, sigma is the conductivity, 1 on alpha, which is where alpha is the radius of the core, inner core, 1 on beta is the radius of the outer core, right? And I plug all this information into my propagation constant, and now what I'll do is I'll differentiate again with respect to A. And after you do some algebra, I mean the algebra gets a little bit messy, so I've done that all for you. What you can actually show is this equation has a minimum loss when the log, natural log, which is log base C, on B divided by A equals to 1 plus alpha 1 on A beta. And if you actually solve this equation, which is a nonlinear equation, if you solve it, you find that this equation has a solution when beta on A is equal to 3.6. Okay. What does that all mean? Well, if we do that and assume that it's air-filled again, we find that the characteristic impedance for minimum loss is 77 ohms. And if you remember, for all of you that have looked at those coaxial cables that plug in the back of your TV or the back of your Foxtel box, it's actually a 75 ohm coaxial cable. It's not actually a 50 ohm. The reason is that provides you the minimum loss, right? So the problem now, we've got a dilemma. 30 is maximum power, 77 or roughly, you know, for 77 is the same as 75 as far as engineers are concerned. So 75 is the minimum of the characteristic impedance which gives us minimum loss. Well, where does the 50 come from? Well, the 50 comes from, hey, we want somewhere between maximum power and minimum loss, so let's just choose somewhere in the middle. So there's nothing magical about it. It's no God-given fact. It's just something that people did a long time ago, and for whatever reason, we've fallen in love with it, right? And we constantly use it. Now, if you're designing your own components on a chip, there's no reason for it to be 50 ohms. You should choose it so that it gives you the best performance for your particular application. Now, the only time you might want to use 50 ohms is if you're interfacing to the real world, because it allows you to plug in standard test equipment which is designed in order to have input impedances of 50 ohms. So that's the only time you should be using 50 ohms, right? Other times you should choose whatever the characteristic impedance is that gives you the best performance for your particular application. Yes?
Why would you use 50 ohms instead of 75? It's got both cables on the w3l1. It also has 75 ohms cables, so how would you choose it?
I mean, because the test equipment's usually 50 ohms. That's the only reason. I mean, it's bizarre, but it's just what everyone's chosen. People have standardized on it. But the point is, there's nothing magical about it. And for whatever reason, everyone chose it, and every student I know, or even work colleagues, they constantly regurgitate 50 ohms as if it's some God-given fact. And if you don't do 50 ohms, the sky's going to fall in. And the answer is no, it ain't. It's just that, you know, if I'm doing it on a chip, and if I'm high frequencies, probably, you know, 200 or 500 ohms is better if I can actually get it. But the challenge there, of course, is I've got whatever I design also has to meet, you know, your DRC or design rule checks, because usually on chips or PCB boards, there's usually a minimum trace that you can actually produce. But usually high impedance is good because you're pushing voltages around rather than power. Whenever you're pushing power around, you've got power dissipation issues, you've got a whole bunch of other issues that you've got to deal with, which you don't want to be doing. Okay, that was just a little bit of intuition and a little bit of fun, engineering fun. Hopefully you enjoyed it as much as I did. Okay, so we went through a lot of pain so far talking about transmission lines. So the question is, why did we do all this, right? So all of a sudden, we said, you know, transmission lines are important, and we use them to transfer energy, and they're a significant portion of the wavelength, and there's certain standing wave ratio patterns on it. But so what? Why do I care about that? And why is it relevant, you know, to what you may be doing in the design or the manufacturing of certain components? So let's go through some analysis. Now, you've probably seen all this before, right? Now, what I'm going to try to do is describe it in a slightly different way, which might be able to give you some different insights. Okay, so what we've got is a piece of transmission line, and we've got a load, right? And for argument's sake, let's assume that this source or generator that we're connecting up to this transmission line has the same source impedance as the characteristic impedance of that line. Okay? And what we say is we launch a wave into this transmission line, and we all know, we've heard it so many times before, that when there's a mismatch in impedance, there's going to be a reflected wave, right? So all the energy is not going to be stored, or is not going to be all be transmitted or accepted by that load. And what we're going to try to do now is work out the analysis in order to work out how much of that power is being reflected into that load. What does it mean in terms of, if I've got a transmission line connected to a load and I'm looking at it at a particular distance, what does that transmission line look like, and what does that impedance look like? Okay? Now, can anyone guess, right before we go through all the analysis, suppose I had a load, I don't know, let's for argument's sake say 75 ohms, and I connected it through a transmission line which had a characteristic impedance of 50 ohms. And suppose the length of that transmission line was a quarter of a wavelength. Does anyone know what the relationship between characteristic impedance, load impedance, and the length of the transmission line is relative to what I will see if I connected something to the end of that transmission line? Has anyone done that analysis before or gone through that analysis? Okay, let's go through it then. But we all know, who doesn't know that impedance that I see will critically depend on the length of the transmission line? So everyone knows that, right? Yes, perfect. Okay. Good. All right, so let's go through it. We said that the voltage wave, so we launch a voltage wave onto this transmission line, and we know that at the load line reference plane, or where the load is, there's a discontinuity. There's an impedance discontinuity. And we said that there's going to be some kind of reflection at that point, right? Because the impedances aren't matched. And for argument's sake, what we're going to do is we're going to use our machinery that we've developed in the previous part of the lecture, where we've got this being our essentially our voltage, which is the forward moving voltage wave and the reverse moving voltage wave. And of course, using Kirchhoff's current law, we can also work out the relationship for our current in terms of the voltage wave, the incident voltage wave to this load. And just to repeat myself many times, what we've got is we've got a forward moving component and a reverse moving component. Now, what's important here, because I see a lot of students that get confused, is I'm defining my reference plane in this particular example to be at the load, right? You can always choose your reference plane to be something else. All it means is, well, the equations will change and the relationships that you get will change. But in this particular case, what I'm doing is referencing everything to the load plane. So essentially what I'm doing is giving you what the impedance is going to be at a location here at this particular reference plane, and as we move or increase the length of the transmission line, that is essentially changing the reference plane at which we're looking at and characterising that impedance, or gives us our particular impedance. Now, essentially, if I go through and say just using Ohm's law and say that the V equals IR, in this particular case, V equals ZL times I naught. And we've got the relationships for V and Z, and we plug that into this equation. What we're able to do is work out a relationship between V plus to V minus, which is the ratio of the positive going wave to the reflected going wave in terms of the characteristic impedance of a line to the load impedance, okay? And we define that to be our reflection coefficient, gamma. Now, gamma is a number between what and what? Can anyone guess? 0 and 1. Can you never get -1?
Yeah.
All right, so it's from -1 to +1. Yes, -1 to +1. Magnitude is, if you're saying magnitude is 0 to 1. Okay. Okay. Now, we can rewrite those equations for voltage and current in terms of this reflection coefficient. Okay? So we've got V of Z is equal to the positive going wave, the magnitude of the voltage, the magnitude of the positive going voltage wave, e to the propagation constant plus the reflection coefficient, and the negative reflecting wave. And likewise, we can do the same for the current. Now, what I'll do is I'll introduce some terminology that you usually see in engineering, right, or in engineering speak or microwave speak. The first one is this concept of return loss, right? And return loss is minus 20 log of the magnitude of the reflection coefficient. What is its significance? And what's the minimum and maximum value of that return loss? And why? Who can tell me? What's the minimum value? 0. Really? Or is that the maximum value? Okay, so gamma is magnitude of gamma is a value from 0 to 1. So therefore the maximum value of magnitude of gamma is 1. 20 log 10 of 1 is? So that's the maximum. Okay. What's the minimum? Gamma equals 0. So 20 log 10 of 0 is? Minus what? Minus infinity. So the return loss goes from 0 to minus infinity. Okay, great. What does minus infinity mean? If you have a return loss of minus infinity, what does that mean? Sorry? Is that what it means? Or does it mean the opposite? So gamma is 0, which means nothing's reflected, which means all the energy goes into the load. So return loss is essentially how much of that power comes back and hits you. You put energy in, how much of it's coming back to hit you? Right. And what's its maximum? 0, which means essentially you put all the power and it just comes back and hits you. Can anyone give me an example of a transmission line or a load where you would think the return loss would be 0? So essentially what I'm saying is you put energy onto this transmission line, bang, it all comes back to you. What are a couple of examples or an example of that? Yes?
When the transmission line is open circuit?
Open circuit, yeah. Right, so you can have a transmission line, it's open circuit, all of a sudden the power's going across the transmission line, all of a sudden it hits, can't do anything, it's open circuit. So all the power has to come back, right? Assuming that it's a lossless transmission line. Okay, perfect. So what we're saying here is the return loss can be a number between 0 and minus infinity, and ideally what we want is the return loss to be minus infinity. But in many cases we can't achieve that. And generally when we're designing, for example, antennas and components like that, it's usually hard in order to be able to get the return loss or the matching of that antenna to be so good across a wide bandwidth. And essentially what you do is you usually say that my antenna, because we're engineers, not mathematicians, right, is matched usually if the standing wave or the return loss is better than minus 10 dB. Right? That's usually an intuition or something that you use, because generally it's really hard to match an antenna over an extended bandwidth. So usually if you've got the reflected power, or essentially it's accepting 90% of the power that you put on the line, then you say, well, that's good enough for engineering purposes or for government work, the way that I'd like to say it. Okay, so then the next thing that we define is this concept of voltage standing wave ratio, right? And that's something else which we'll go through in a few slides, especially on how to be able to calculate it using a Smith chart in probably 3 lectures' time. But essentially what the standing wave ratio, or voltage standing wave ratio is essentially the ratio of the maximum voltage to the minimum voltage that you expect on that transmission line, right? And that has certain implications in terms of if I'm measuring my, the voltage at a particular location on this mismatched transmission line, or the load's not matched to the characteristic impedance, what I would expect is, depending on how I move across this transmission line, it tells me the ratio of the minimum voltage to the maximum voltage. And the other reason where it's important, or why it's important, is sometimes you might be connecting gates, logic gates, or something else which is sensitive to that particular transmission line. So therefore it also indicates to you what potentially the maximum voltage could be, right? Because if you know roughly the ratio of the input to output voltage, you know that if you can make an approximation that the transmission line is roughly lossless, and you can say, well, I'm putting in X volts, you can actually say, well, this is the ratio that I would expect. So this is the maximum voltage I would expect on this particular transmission line. Okay, excellent. All right, so we're all excited now. Now, what I'll do is, we had this transmission line, so let's go back to it. We had this transmission line. We said that there's a load. It's connected to the generator with a transmission line of a particular characteristic impedance. And if we do that, we can rewrite at any particular location on that transmission line what we expect the impedance looking into that transmission line to be. Right, all I've done is I had my relationship for essentially voltage and currents here. And what I've done is I've said, well, what I'm going to do is I know the relationship between voltage and current. I'm going to divide the ratio because that's just Ohm's law, and I can work out the impedance. And now what I'm going to do is I'm going to rewrite it in terms of length of transmission line. Right, so I've got a load connected, we've got connected through a particular section of transmission line. And because, as I said, we've got the reference plane is relative to the load, what I do is any length of transmission line becomes minus L, right? Because I'm moving away from the load towards the generator. Okay, and if you do a little bit of algebra, what you can convince yourself is that now you've got the input impedance of this system, transmission line of particular characteristic impedance, plus a load impedance, which is given by this relationship, which you've probably seen, as I said, hundreds of times before and probably sick of it already. Now, why is it useful? Can anyone just remind me? I've already said this, but why is it useful? Because you tell me the length of the line, you tell me its characteristic impedance, you tell me what I've connected up to it, and I can tell you what its input impedance is. And consequently, if I'm connecting a source to it with a particular source impedance, I can actually tell you how much of the energy is going to be reflected at that interface. So I can actually tell you how much of the power is actually going to go from the source or from the generator into this system, how much of it's actually going to go onto, or what percentage of it's actually going to be accepted and travel along this transmission line. It's essentially telling me what the impedance is. All right, and what I'd like you to do is also think about some other examples. How are we doing for time? We've still got 15 minutes, perfect. Okay, so now I'm going to go through one of your, there's a couple of cases that we need to consider. One of them, which is always interesting, is a short-circuited transmission line, right? What does it mean when I say I've got a transmission line which is short-circuited? Yeah? Sure. Essentially, I guess I'm probably not asking the question properly, but essentially what I'm asking is I'm putting a zero load impedance, a zero ohm impedance at the end of the transmission line, right? And also what I'm saying is that the voltage at the end of this transmission line, if it's a zero ohm impedance, it also tells me that the voltage there needs to be what? Zero, right? Ohm's law. So what we do is we go through this equation. Let's assume ZL equals to 0, and we substitute it into our equation for input impedance. We can actually see that the input impedance equals to J, Z0 tan beta L. Okay, interesting, but what is its significance? Other than we've got a very interesting mathematical equation written in terms of tan times beta, which is the wave number, times the length. What can someone tell me about the tan function? Tan. You've got tan, right? Which is opposite over adjacent. What can you tell me about its minimum and maximum values? Guys, this is, year 10 geometry, right? All right, so what's the minimum and maximum of sine? -1 to 1, right? Okay, and it's 0 at the origin. Cosine? Right. Tan? Okay, interesting, right? Interesting. Because what it's saying is that the input impedance of this particular line is complex, but it goes from -infinity to positive infinity. Wow, right? But I'm connecting, but what's important is I've connected a short circuit, right? It's 0 ohms. I've connected 0 ohms to this transmission line, but notwithstanding the fact that I've connected a 0 ohms to this transmission line, the input impedance that I'm looking into it can go from -infinity to -infinity, which is, at least the first time I saw it was like, oh wow, geez. I mean, it actually gives you some interesting ways at which you can actually start producing very high impedance or very low impedance components if you needed to. But it also says, hey, you can also, if you've very badly mismatched a line, and you can actually make it look like infinite impedance. Okay, so what we'll do is I'll go through the graphs here, and I apologise, this is me drawing things out, and I'm old, and so my hands are getting, pretty hard to draw, or arthritic, I should say. So therefore, what I've done here is actually shown you what the relationship is between voltage and essentially along the distance of that line, right? So therefore, we got, all I've said is V of Z divided by V plus. This is essentially the relationship of voltage, or the voltage on that line, across that line, right? So you can actually see and determine what the voltage is as a function of the voltage which you put into, the zero voltage that you put, that you would expect at the load, and V of 0 being the voltage that you put on the line, or V plus being the voltage that you put on the line. Likewise, you also can determine the current, and as you would expect, at the end of the short circuit, the voltage is 0, but the current is maximum, right? So if you're looking through doing these calculations and determining, hey, have I got the calculation right? One of the things that you should also think about is, hey, if it's a short circuit, voltage is supposed to be 0, but if I've got a short circuit, that's where the current is maximum. So that gives you an insight in being able to know what the phase relationship is supposed to be between these quantities, between the voltage and the current. Now, what I've done, of course, is then worked out the ratio of V versus Z, which is essentially just the tan beta beta Z. And what you can actually see is depending, you know, when you're at the load, the impedance is 0. As you're moving further away from the load, going towards a quarter of the wavelength, the impedance is getting larger and larger and larger and larger and asymptoting to infinity. Once you cross the quarter of wavelength, you get a phase change, and essentially the impedance looks like minus infinity, and it begins increasing from minus infinity to 0 back to positive infinity. Right? So essentially what it says is, using a transmission line, one of the key concepts here is that you can actually use a transmission line in order to be able to transform the impedance of a particular load. Right, and that's one of the tricks that we're going to use in our analysis in order to do impedance matching. Right, when we're talking about Smith charts and impedance matching and you know, various sections of transmission lines and shunt lines and the like. Okay. Now the question I've got is, all right, so we've talked about short circuits. How about open circuits? All right, so if we've got an open circuit, we expect the impedance to be what at the load? Infinite. Okay. What do we expect the voltage to be at the load, which is open circuit? Maximum, right? And we expect the current to be exactly equal to 0. Okay, so essentially all I've done is gone through the same process where I've got the voltage and current, and essentially what I've done is I've gone through and done a little bit of mathematics for you and shown that the input impedance of a short circuit goes as cot beta Z. Now, does everyone know what cot is? 1 on tan, right? All right. So essentially, you can go through and convince yourself that, you know, unlike a short circuit, an open circuit achieves a maximum at Z equals 0, and the minimum occurs at Z equals minus ln2. All right, and of course, you go through and you can draw all this out for yourselves, and because you've actually seen how terrible I am at drawing, you can actually see that the current is 0 at Z equals 0, Z equals to minus lambda on 2, and Z equals lambda, right? So essentially, whenever you go half a wavelength away, you're actually going through the current being 0 for this particular transmission line. All right, so what I would suggest that you do is, whenever you've got a few minutes spare, actually draw what a cot function looks like, work out what the voltage, the current, and the input impedance is. Okay? And that way you can actually at least know, for example, if you had a dipole connected to a transmission line, right, which is essentially an open circuit, you can see that if you, as you increase between, you know, across wavelength, you know, that there are, you know, sections which we've done where it's actually radiating, but at other frequencies it actually looks like an open circuit, and you start getting some interesting behaviours, right? And you have to be able to contend with that under certain circumstances when you're actually building your system. Now, the last thing I wanted to talk about in this lecture is transmission coefficient, right? And essentially, what we've talked about so far is the reflection coefficient, which is the power that is reflected from a load or from a particular interface. Of course, if we've got a transmission coefficient, we must also, if we've got a reflection coefficient and energy and power is conserved, we must also have part of that energy being transmitted, right? So therefore we know that there's a relationship between transmitted power and reflected power, and essentially all it is the transmitted power plus the reflected power is equal to 1, right? Conservation of energy, which is conservation of energy, and power is the time derivative of energy. Okay, so if we go through the calculations, well, what we can actually see is if we've got an arbitrary interface between characteristic impedance and the load, we've been talking about reflection coefficient, but of course we can work out the component of power that's actually absorbed into that interface, and we define that to be the transmission coefficient. You can go through and convince yourself that the relationship of what essentially the transmission coefficient is, how to derive that transmission coefficient. And importantly, what you've got is this concept of insertion loss, right? We've talked about reflection loss. You've also got now this concept of insertion loss, which is actually how much of the power is actually absorbed into your load or is actually transmitted to that system, right? Because sometimes as engineers, someone might actually tell you this is your reflection loss, someone might actually tell you what your reflection loss is, but there's a relationship between between insertion loss and transmission loss. Sorry, reflection loss and insertion loss. That's the only thing that I wanted to say there. Yes? You don't have it. Okay, let me do it again. Sorry. I'll update it. And that's the end of the lecture. I don't know what's happening. I put them through the photocopier and get them to scan to me, and just I put them up. So I'm surprised that it hasn't been included. But these slides, what I'll do is update it. Now you should have the updated slide 6, which I've made sure it does have all the slides in it. What I'll do is I'll put it through the photocopier again, and hopefully the pages don't get stuck together, and it actually photocopies it all. All right, but importantly, what I want you all to do is I've put example problems up on LMS. Please go through them. I know that the course is difficult, and a lot of you might be finding it a little bit challenging, but if you do the problems or the questions, at least that way you know what you need to know. And as you can imagine, test questions or exam questions are going to be very similar. So make sure that you do them. All right, excellent. Yes?
It says in the workshop that we'll cover that content in the lecture. Is that
Okay. No. All right, okay.
And I have some questions.
Okay.
What is B and what is Z?
Z is length along the coordinate, and B is 2 pi on lambda.
B is pi
On lambda.
This is the wavelength.
Wave number.
Wavelength.
Wave number. Yeah, lambda's wavelength, and 2 pi on lambda is the wave number.
Okay, Z is the length
Le-
through the Z axis.
Yeah, Z-axis, no, but the transmission line, and what I've said is, depending on where the reference plane is, it's relative to the load.
Yeah.
Okay? And that's why I was emphasizing it.
This is the length of the transmission line.
If length of the transmission line, but depends on where my reference plane is. If my reference plane is at the generator, lambda's positive. If my reference plane is at the load, going towards the generator is minus lambda.
Minus.
Right? Depends on what I've defined as my reference
The
planes.
Z can be plus or minus. That's what you mean.
That's right, but here I'm defining it relative to the load, so it becomes negative.
Okay.
Sure.
This one, I'm not sure why is this epsilon or epsilon dash.
That's supposed to be epsilon 1 dash. Yeah.
Okay, thank you very much.
I've already tried those problems.
Should have been easy.
Yes.
Yeah, they're not too hard.
Like if you understand those formula, you find out where it is and
Yeah.
understand what's inside.
Yeah.
The meaning of those parameters is easy.
Yeah. It's. I mean, what I'm trying to do two things, right? So I'm trying to make. What I'm trying to do is I'm trying to teach you a whole bunch of concepts that you need to know, but then I'm also trying to do it in such a way that you guys also get good marks. So therefore, it doesn't affect your scholarship scores if you want to do a PhD or something. So I'm trying to trade
In
right.
the beginning, I'm really afraid of you are going to test us about those concepts, how to get those concepts.
No. It's not. This is engineering. It's not. It's not science. So what I'm trying to do is, what's important is for you to have an understanding of the concept,
Yeah.
how to apply it,
Yeah.
and what it all means. That's what's important,
Correct.
right?
Yeah.
The derivation, what I'm doing is so therefore it gives you an insight, so therefore you can actually say, oh, it comes from Maxwell's equations. This is what Maxwell's equations is. Oh, hey, I've got this concept of inductance. Oh, inductance is related to magnetic field. Oh, wow, you know what I mean? But that's what I'm trying to do. So therefore, if you're designing an inductor, you can actually say, ooh, I'm trying to maximize the magnetic field.
Yes.
And that's why it's going to give me the maximum inductance.
Okay. But do you see